So we've talked around the concept of kinetic energy and we've said that it's the energy of movement, but we need to expand on this definition of kinetic energy to see how the work is influencing it. Because yes, it's an energy of movement. Yes, as you push something, it's increasing its kinetic energy, its energy of movement, but how could the velocity of the car change if you put a mass on the top of the car? So we have this situation, but what if I were to put it here? Okay, if I put another mass right here, would we expect the car to have the same change in velocity as it goes through the photo gates? And the answer is no. Even though I exert a force on it over a certain distance or did work, the mass of this particular car is going to matter in terms of determining the velocity of between these two cars. So it's not quite as simple as what we said before, where okay, I increase the work and therefore I'm going to increase the energy of movement. You can't quite take it out to velocity quite yet, which is what we really want to do to be able to relate it to what we learned earlier this semester. So now we have the energy, the kinetic energy, and that says our equation Ke equals 1 half mv squared. Ke stands for kinetic energy, and that is defined as the energy of movement. And it is equal to 1 half the mass velocity squared. So in order for an object to have kinetic energy, it must have mass, which all objects that we're going to study this year have mass, and it must be moving. In other words, it must have a velocity that is not zero. Okay, it can have a really small velocity, it can have a really high velocity, but it must have a velocity. So this right here is your kinetic energy equation, and once again, kinetic energy can be calculated from mass, which can be measured with a triple beam balance, and then you can use a photo gate or a meter stick to figure out the velocity. One of the things that you need to realize though is that kinetic energy is once again an energy, so it is measured in joules. All energy is measured in joules. Okay. So, example B1. It says you have a 2,000 kilogram car that runs out of gas and comes to a stop. The car must be pushed to the nearest gas station 500 meters away. A force of 200 newtons is applied for 10 meters. What is the final velocity of the car? So this is actually a question that's going to require us to do the work energy theorem and our new knowledge of what kinetic energy actually is. So what I want you to do is we take a look and say, okay, we have a 2,000 kilogram car. It's at a stop. So if it is at a stop, that's going to come into play in just a second. So the car must be pushed to the nearest gas station 500 meters away. A force of 200 newtons is applied for 10 meters. What is the final velocity of the car? So we're trying to figure out what the final velocity of the car is. So if you kind of draw this out, this car is at a stop and you've got somebody who's got to exert a force on it. They've got to push it 500 meters away, but what it says it only pushes it for 10 meters. So although there's there's two different distances here, this one is irrelevant because it's saying you only exert the force for 10 meters. Even though it's 500 meters away, you're only doing the force for 10 meters, so that's what's important. So you have you have mass is 2,000 kilograms. You have a force of 200 newtons. You have a distance or displacement of 10 meters. Okay, this is also really key here. This stop term. So even though it says it comes to a stop, realize that that is the initial starting point before you push. So the initial velocity of the car is zero. So now let's look at what we've got. Our equation is W equals delta KE. Now, I'm going to have to expand both sides of this equation. So instead of work, I'm going to put what work equals, or force times distance. Okay, instead of delta KE, what I'm going to do is I'm going to put 1 half m VF squared. Okay, in other words, 1 half the mass times the final velocity squared. What that represents is that represents the final kinetic energy minus 1 half m VI squared, which represents the initial kinetic energy. So you can start to plug in the numbers now, and you can say, okay, you can plug the number. But what's really important in this particular case is you realize that the initial velocity was zero. So if I take zero and square it and multiply it by m, no matter what m is, it's going to be 0. And then I multiply it by half, and it's still going to be 0. So what you should realize is this whole second term right here is going to cancel out. And I'm just left with FD equals 1 half mvf squared. So now we can plug in our numbers, and we can say, okay, well, force, this is 200 times distance, 10, equals 1 half mass, which is 2,000, and then final velocity squared. So you've got 200 times 10, which is 2,000, and you've got 2,000 here. Since I have 2,000 on both sides of the equation, it will cancel out. And what I'm left with now is 1 equals 1 half VF squared. Okay, multiply both sides by 2, and you get 2 equals VF squared. You need to take the square root of both sides, and you get the final velocity is the square root of 2, which is 1.414 meters per second. This is example B2, and it says you have a 10 kilogram rock which is dropped off a 14 meter tall cliff. What is the kinetic energy of the rock just before it strikes the ground? So this is an interesting question because it makes us have to know a little bit of information from the first 6 weeks, and that is our initial kinematics equations. Because it says what is the kinetic energy, so I'm trying to solve for KE, and in order to solve for KE, I need to know the formula. Kinetic energy is 1 half the mass times the velocity squared. So that's what I really need to do in order to be able to solve this. But the problem is it doesn't tell me the velocity. Instead, it tells me the distance. So what I'm going to do is I'm going to go ahead and have to solve for the final velocity right before it strikes the ground. Whenever we do this, we can say you have a rock that is at the top of the cliff and it has an initial velocity of 0. We were interested in the final velocity of the rock right before it strikes the ground because I want to know what the kinetic energy is right before it strikes the ground. If I asked for the kinetic energy at the top, it would just be 0 because the rock is initially not moving. So because of this, I need to know what this final velocity, or this VF2 term is, not VF squared, but the final velocity at the end. So I know that the initial velocity was 0. I'm interested in finding the final velocity. I know that the acceleration is the acceleration due to gravity, or negative 9.8 meters per second squared. And I know that the displacement of the rock in this particular case is going to be a negative 14 meters because it falls from the top to the bottom. So I can say that I do not have any sort of use for time. So remember, if you do your IFDAT, IFDAT, you have the initial, you have the final, you have the displacement, you have the acceleration, and you do not care for the time. So because of that, you're going to choose the equation that does not have time in it, or VF squared equals VI squared plus 2AD. Okay, our initial velocity term is 0, so that term is going to cancel out. So instead, what I'm going to be left with is the final velocity squared, which is what I'm looking for, is going to be equal to 2 times negative 9.8 times negative 14. And when you take those and you multiply them out, you get, hold on just a second, 2 times 9.8 times 14, you get 200, you get the final velocity squared is equal to 274.4 meters per, well, there's no unit really at this point. You've got to take the square root of both sides to solve for the velocity. And when you do that, you get, hold on a second, you end up getting 16.6 meters per second. Now when you do that, that's not really what you're looking for. Remember, really what you're looking for is the kinetic energy. So what you can do then is you now have the final velocity, which allows you to use the equation KE equals 1 half mv squared. So you would plug in, you'd say equals 1 half the mass, where the mass is 10, and then you have the velocity squared term. Now, I would highly recommend that you not use 16.6 here because that's a rounded version of what we did. Remember, the final velocity squared is actually a more accurate answer because we didn't have to round it. It was actually like 16.5650233, and it keeps going. So to get the most accurate answer, I actually want to take my final velocity squared term and put it in here because it's already squared. So you put in 274.4. Whenever you do that, you can now multiply it out. Remember, I've already squared the velocity, so I don't have to deal with it anymore. So I would just take that and multiply it by 10, and then divide by 2, and I get a kinetic energy of the rock just before it strikes the ground of 1,372 joules. Now, we're actually going to talk about a little bit easier way to do this after the next lesson, because now we're going to talk about gravitational potential energy in the next lesson. It makes it a little bit easier. But for now, you can do it using kinematics. The last question that we're going to talk about now says you have a 6 kilogram bowling ball thrown with a velocity of 20 meters per second. How fast must a 0.140 kilogram baseball be thrown to have the same kinetic energy? And this is one of these questions that you tend to see on a test where it's got twice as much mass and it has to have half as much velocity as what most people think because it's got twice as much mass. So here, if you were to look at the mass ratios, 6 divided by 0.14 says that it should be, this is about 43 times bigger. So the bowling ball is about 43 times more massive than the baseball. So a lot of people say, oh, okay, well then the baseball's got to have to be moving 43 times more faster. It's not the case. I just want to tell you that that's what a lot of people think, and that's wrong before we actually do the math. So basically what I have is I have two kinetic energies here. I have the kinetic energy of the bowling ball, and I have the kinetic energy of the baseball. And because of the circumstances of the question, I know that those two kinetic energies are equal because the question says they have the same kinetic energy. Normally they would not. Like if you were doing an actual experiment with a baseball and a bowling ball, they would almost never have the same kinetic energy. But in this particular case, they do. So what I can do is I can say the kinetic energy of the baseball, but base, equals the kinetic energy of the bowling ball. Those two things are equal. So now I can say 1/2 the mass of the baseball times the velocity of the baseball squared has to equal 1/2 the mass of the bowling ball times the velocity of the bowling ball squared. If you look, 1/2 is on both sides. So since 1/2 is on both sides, it cancels out. You have the mass of the baseball. The mass of the baseball is 0.14 kilograms. You do not know the velocity of the baseball, which is still squared. That has to equal, on the other side, the mass of the bowling ball. The mass of the bowling ball is known, and once again the 1/2 canceled out. So you've got 6 times this 20 term squared. Okay, so now in order to solve for this equation or this question, you're going to divide both sides by 0.14. Okay, because you're starting to isolate the velocity of the baseball term. So then you would go to your calculator and you say, okay, 6 times 20 squared divided by 0.14, and you get 17,142 equals the velocity of the baseball squared. Remember, you don't want the velocity squared, so you've got to take the square root of both sides. And when you take the square root of both sides, you end up getting a velocity of 131 meters per second. So even though the baseball is 43 times smaller than the bowling ball, if you were to compare their velocities, the velocities are much closer. In fact, they're only about 6.5 times different. In other words, it's actually a square root of it, of the mass. So what you should take from this example is that whenever you're looking at kinetic energy, the velocity of something is much, much, much more important than the mass of an object.